it, moment of inertia is very, very important thing to describe the motion of a rigid body. So first thing, what is the moment of inertia? The mass moment of inertia is a measure of an object's resistance to rotation. Or we say the moment of inertia is the resistance to the change of angular velocity. We know that the mass, only the mass is a measure of our object's resistance to translation. But here we have the mass moment of inertia, which is to measure the resistance to rotation or the resistance to the change of angular velocity. We have known that angular velocity, angular acceleration, actually is to describe the motion of rotation, right? So we know the mass moment of inertia, the definition, how to calculate it. If we know the object's mass and we know how it is distributed, then we can calculate mathematically. First we use big I to indicate the mass moment of inertia, and dm is actually the mass of the element. The mass of the element r is actually the radius. We use actually acts as the moment arm of the mass element. The mass of the element is equal to the density times its volume. So after we find out the r squared times dm, we integrate over the entire rigid body, we can find out the mass moment inertia of this rigid body about the z-axis. Because we know that when we talk about rotation, it's very, very important that we need to indicate the axis, right? We need to indicate which axis the rigid body is rotating about. So similarly, here, the mass moment of inertia is to measure the resistance to rotation about an axis. So when we talk about the mass moment of inertia, it's very, very important. You need to use subscript to indicate which axis you are talking about. This is the definition, okay? This is the definition, okay? So according to the definition, we know that the mass moment inertia is not only related to its mass, but also related to how the mass is distributed, right? Okay. Also, according to the definition, the mass moment inertia differs for each axis about which it is calculated. Just like when you rotate, when you try to push the door is rotate about its axis, right? We know that different axis of the door and so we need to apply different force to open or close it, okay? Because the object's resistance to rotation will be different. Sometimes, here, should use, we also can, some books use J, you can use I or use J to indicate the mass moment inertia, okay? According to the definition, the mass moment inertia is always a positive scalar, which is only determined by the position of the axis. Again, is the position of the axis is very important. So we have the subscript to indicate the position of the axis. And also, the mass moment inertia is dependent on the mass distribution of the rigid body, but it is irrespective of the motion state of the rigid body. Okay, whether it is static or it is rotating, the mass moment inertia is same. Okay, the mass moment of inertia of the rigid body must indicate which axis it is. We just address this again and again because really it's very, very important. Okay, otherwise it does not make any sense. So how to calculate the moment of inertia? Here we just start from one dimension and one dimensional rigid body. Okay, we just here calculate homogeneous slender body. That means the density is a constant. Okay, for the entire body. The slender, the length is equal to L, its mass equal to M. We need to calculate the moment of inertia about z-axis and z1 axis. Here you see we have two different axes. We need to calculate the mass moment of inertia. Okay. So according to the definition, first we need to take an element. Okay, we calculate the mass of the element. The mass of the element is equal to the density. Density is equal to the mass divided by the length because here is one dimensional. Okay, times the volume because one dimensional is dx. And so, because the distance to the x-axis of this element is x, so sorry, in the textbook we use I. Okay, we don't use J. In the textbook use I. Okay, so the mass moment inertia about z-axis, Iz, z subscript to indicate the axis, which axis we are calculating, right? And this one will be x squared is actually x is the distance from the element to z-axis. dm because for every element will be m over l. The density is a constant, so we can take it out of the integration. And the lower limit of the integration from the definition of the coordinate system starts from minus half L to positive half L, and we calculate this integration. We know this is equal to what? For this integration, and then minus L. So we can calculate this. You should know how to integrate this, right? It's not difficult, okay? For this one, do you have any question about this calculation? This one. This one is actually the integration should be what? And lower limit, upper limit, and then we can calculate it. After the calculation, we know the integration about z-axis is equal to 1 over 12 m L squared. M is a mass. L is the total length of this slender rod. Okay. Similarly, we can calculate the mass moment inertia about z1 axis. Okay. So z1 axis here, the only difference is the lower limit and upper limit, right? Again, we establish the coordinate system. Here, the origin located at the end, okay? So the integration start from 0 to L. And here it's the same. X is the distance from the element to z1 axis. And then we calculate the integration. We will obtain the mass moment inertia about z1 axis is actually equal to 1/3 ml squared. So you say about different axes, the mass moment inertia is different. Again, it's very, very important. When you talk about the mass moment inertia, you need to specify the axis. So we can continue the study. Homogeneous thin circular plate. Again, it means density is a constant everywhere. And for the circular plate, for the circular disk, the radius is given as big R. The mass M is mass. Axis, we choose axis pathing is mass center. Okay, we need to calculate the so we need to calculate the mass moment inertia about the axis. So this time we just need to take the element like just here. We take the element area, the element mass here. This is the element. Now, this to calculate the density. The density is equal to the total mass divided by its area. And then this one, what means this one? This one is actually the though times the volume. Volume because here is 2D, so it's area, right? The area will equal to 2 pi r. R is actually the distance to the center mass, and dr, okay, is the um, thickness of the circular, okay. So we have this, the mass of the element, and then times r squared. R squared is the r is the distance to from the element to the mass center. Why we choose this one instead to choose like this way, dr d theta? Why? Because everywhere they have the same distance to the axis. That's why here we can calculate the mass moment inertia about the axis. Well, again, we need to take the integration starting from 0 to r, okay? And then it will equal to 1/2 times mass times r squared. So this is to uh, give you the examples how to calculate the mass moment inertia for some very simplified geometries. Here, the figures below show the mass moment inertia formulations for two flat plate shapes commonly used when working with three-dimensional bodies. So we already calculated this two-dimensional, one-dimensional, two-dimensional, but generally speaking, in the real life, in practice, we will meet with three-dimensional bodies, how to calculate them. So we need to choose differential element when you choose. Uh, it's very important to choose the different ratio element to simplify the calculation. Okay, so for the same plate, like here you say for the z-axis, the mass moment inertia will be not only related to a, but also related to the side length b. About the x-axis, about the y-axis, you say it's different. So again, you say it's very important to specify the axis. You are calculating the mass momentary inertia. Okay. So how to choose the differential element? For this axis, it's easy, right? A cubic, and for x-axis, same. And the only difference is the integration range. Okay, the lower limit and the upper limit were different about different axis. Sorry, here just earthquake. Okay, earthquake. Just wait a minute. Okay. Sorry, we are experiencing earthquake. Okay, what here? Okay, finished. Thanks. Thank God. Okay. Ah, just give me 1 minute. Okay, 1 minute because it's a little bit scary. Okay, so we're back. So I know some of you, I don't know whether you have experienced earthquake, but here in Sichuan, in Chengdu, we have experienced quite huge earthquake, very serious earthquake in 2008. Okay, we have lost a lot of people, but Chengdu is quite safe, so don't worry. Even just like right now, and yeah, it's shaking. Okay, I'm a little scared, but I know everything will be okay. So we'll continue our um, study. Okay, so here it's very important to indicate the sorry again the earthquake. Give me 2 minutes. I need to call my mom. Okay. Okay, let's get back to the class. Okay, so the network is okay. Can you hear me? The network is okay. Are you there? Thank you very much. Okay, so let's continue our study. Okay, okay, let's continue our study. So no problem. Yeah, the earthquake, but I think it's okay. Everything will be fine. And Chengdu is quite safe, so no problem. So we continue our study. Okay, so the differential element, how to choose the differential element is quite important. And so let's say how to continue. So it's very important to choose the differential element. So let's say how to choose, just like shells element. Okay, here, sorry, we just like here, only symmetric bodies having surface generated by revolving a curve about the axis will be considered here. So sometimes we need to choose shell element, just like here. That's now actually we choose a shell element. Okay, if a shell element have a hat z, oh, I would not prefer which. Okay, the having a hat z, radius r, the radius r is equal to y. Here we define the coordinate x, y, z. We try to calculate the moment inertia about z axis. And so here we choose the shell element. The radius r, you see, we say the distance to the z-axis of the element will be equal to r everywhere. Here equal to y. Okay. Then the volume m, element and thickness dy is chosen for integration. Okay, so volume element dv is equal to 2 pi y. 2 pi y is the parameter of the shell, okay, of the circular right. Parameter of the shell, 2 pi y z dy. Okay, 2 pi y is the parameter, and z is the height, dy is the thickness. Okay, just now we in two-dimensional this right, in two-dimensional shell element. Okay, just the height is equal to 1, but here the height is equal to z. So this element, this shell element can be used to find the moment of inertia about z-axis, because the entire element due to its thickness lies at the same perpendicular distance y from the z-axis. We just talk about this, right? And then sometimes you can choose disk element. Okay, just like here, we choose disk element. So if we choose a disk element, so the disk element have a radius y and a thickness dz, the volume of the element will be equal to pi y square, the area of the disk, right, times dz. Dz will be the thickness. So, and then we can integrate to determine the moment of integration. So, sorry, I forgot one thing here. When you choose the disk, when you choose the shell element, so the differential element is given here. When you integrate, so the lower limit will be start from 0, right? Which one? And r. Am I right? This is r. Am I right? Here, because we need to determine its integration range, right? The lower limit, the upper limit of the integration. Yes, when you choose the shell element, it is, right? Okay. And so here, when you choose the disk element, the the no limit will from 0, z. Okay, z will be 0 and the hat will be h. Okay, so just like we give examples here, the volume shown with dou is equal to 5 per feet cubic. We need to find the mass moment of inertia of this body of the y-axis. So the density is given. We need to calculate the mass moment inertia about y-axis. So here, the y is given as a function of x. We need to decide its mass moment inertia. So first, you need to choose the differential element. Here, obviously, we may choose a disk element. Like, okay, we may choose a disk element. It's symmetrical. Okay, so when we talk about 3D, we only talk about symmetrical geometries. Sure, if it's not symmetrical, you need to choose the element and then calculate dv as equal to dx, dy, dz. It will be a triple integration. It will be a little bit complicated. So that's why here we only talk about the symmetrical geometry because the integration will be simplified as one dimensional. Okay. So first, we decide that we choose the disk element, and then we calculate the dm. And then for this dm, and we can calculate its mass moment ratio, and then we integrate, okay? But here, actually, we just skip this step. Why? Because for the disk element, we know that this disk element, the mass moment inertia of this disk about y-axis will equal to 0.5 m r squared. Okay, so we can calculate the mass moment inertia about y-axis for this disk element is equal to 0.5 x squared dm, and then the dm is equal to the density times its volume, and its volume is equal to pi x squared is the area of the disk times dy is the thickness. And then we can calculate the integration for the whole rigid body, okay, also whole subject, and the no limit for the y starting from 0, and then the hat will be 1, and then we can calculate the mass moment inertia. So here it's very important that you need to decide the differential element and then calculate the mass moment inertia for the element and then take the integration. Okay, so sometimes you can do it step by step. Okay, you can do it step by step for this mass moment inertia because for this disk and we have calculated the mass moment inertia of this disk about y-axis, right? Just from this example. Right, here we calculate the mass moment inertia about this the axis. Here, right, mass times the its radius, okay, square, okay. Sometimes we just when we just look when we just look the just for the textbook, we can find out the mass moment inertia about its mass center for most simple geometries. But sometimes we not only need to know the mass moment inertia about the mass center, we need to find out the mass moment inertia about any axis. So here we have a very important theorem, parallel axis theorem. What is parallel axis theorem? If the mass moment of inertia of a rigid body about an axis passing through the body's mass center is given, then we can calculate the moment of inertia about any other parallel axis. Is very important, okay? The axis should be parallel to the axis passing through mass center. It may be determined by using the parallel axis theorem. Here we need to, again, we need to indicate the axis, okay? Equal to the mass moment inertia about the mass center plus m plus d squared. My m is the mass, d is actually the perpendicular distance between the parallel axis. And so definitely we can just derive this, but here we just skip the derivation process. If you are interested in this derivation, you can just look the book by yourself. Okay, it's very easy. Okay, it's very easy. It's just actually from the definition, just like here, you have this. Element dm, and you have this axis, and you have another axis. Okay, you have another just like here. Okay, so z prime, and then you see here that you have the dm, and then you have the here. Let's just drive it. Okay, so about z-axis, Iz, according to the definition, is equal to r squared dm, right? Dm is the element, the mass of the element. R is actually the radius from the distance from the dm to z-axis, right? And for the z prime axis is actually the axis passing through the mass center, and it should be r prime dm, right? And according to we have the r equal to d plus r prime. Okay, so you can find out this. Okay, look at the book and then check it. Okay, so from the example here, just like we have calculated the mass moment inertia about z axis, z actually passing through the mass center. And we also have calculated the mass moment inertia about d1, the ending point, okay? So we know for the mass moment inertia about the mass center, okay, the axis passing mass center is 112 ml square. And here we can check it. According to the parallel axis theorem, Iz1 equal to Iz plus m d square. D is actually the distance. D is equal to half L, right? And so that's for sure. So this is called parallel axis theorem. It's very important. Okay, so this theorem is very, very important. You will use it often. Okay, never forgot. Here, G is to indicate the body's mass center. Okay, here is a plus. Sometimes we know I, we need to find Ig, and then Ig should equal to I minus md squared. Okay, it's very important, and later on you will use it often and more often. Here we introduce the term radius of gyration. Sometimes the radius of gyration is given. If the radius of gyration is given, and then the mass moment inertia is very easy to calculate. Okay, the mass moment inertia of a body about a specific axis can be defined using the radius of gyration. Here we use k. The radius of gyration has units of length and is a measure of the distribution of the body's mass about the axis at which the moment of inertia is defined. So what this means? This means that if all the total mass of the rigid body is concentrated to the point, okay, concentrated to a point, and then how long or the distance from the axis to the point will be equal to k. We mean they have the same mass moment inertia. What does it mean? Just like here, uh, this is a circular plate, right? We can have Iz, the mass moment inertia about the axis. Okay, and so there is a particle. Okay, we need to calculate the mass moment inertia. If we use the mass, this is a mass m, the mass m, and then the Iz, if they want to be equal with each other, so the distance will be called the duration and radius of duration. So accordingly, if the radius of duration is given, sorry, we can calculate the mass moment inertia directly. Okay. If we have a number of simple shapes, just like disc, spheres, or rods, we just have a combination of these simple shapes. How to calculate the mass moment inertia? Actually, because the mass moment inertia is a scalar, so for composite bodies, the mass moment inertia of the body about any axis is actually just we need to add them together of all the mass moments of inertia. Okay, just like here, we have the rod, we have the disc, and then we need to calculate the mass moment inertia about the axis. All because it's a scalar mass moment, so it's just a sum. Okay, just like for the rod and for the disc. Okay, mass moment inertia is a measure of the resistance of body to. It's easy to choose translation, deformation, angular acceleration, impulsive motion. Which one? Mass is a resistance to translation motion. Mass moment inertia is a measure of the resistance to angular to rotation. So the answer is C, okay? The mass moment of inertia is always positive, negative, in integral value 0 about x perpendicular in the to the plane of motion. Which one? According to the definition, it's integration, right? So it will be always positive. So the two rods, yeah, thank you, B. Two rods assembled as shown, with each rod weighing 10 pounds. We need find the location of the center of mass G and moment of inertia about an axis passing through G of the rod assembly. Here we have assembly. We need to find out the mass moment inertia of the assembly about mass center. But here, first, you need to find out the mass center. How to find the mass center? This is what we have learned before in statics, right? We can calculate the coordinates of the mass center. So first, you need to define your coordinate system. right? You need to define your coordinate system, and here, and the coordinate system, just like here, this is y and this is x, and then we accordingly, the mass center is equal to sigma mi divided by sigma mi, right? Sigma mi is the total mass of the assembly. Okay, mi is the mass of each body. Okay, yi is actually the mass center of each body, right? So it will be, this one will be the mass, okay, of the mass of the rod of the, okay, so sorry, so the mass of the vertical rod and the mass of the horizontal rod, they are equal with each other. So the why, because this is your arranging. Okay, so this is your arranging, and then the x will should equal to 0, right? For the, because it's symmetrical, right? So for the assembly, we only need to calculate its y coordinate. We just downward as positive y-axis. Okay, so for the vertical rod and its mass center, the y coordinate is 1. And for BC, the horizontal is 2. And then the mass times the mass center, the coordinate of mass center times the mass, the sum, and divided by the total mass. This is the mass center, the coordinate of mass center. And then we need to calculate the mass moment inertia about G. How to calculate the mass moment inertia G? We know the G, the mass center about G, the total mass moment inertia of the assembly will equal to Ig, we call this vertical, and plus Ig horizontal, right? But Ig vertical, sure, you can calculate just like using the integration and then calculate the integration. But actually here we can use parallel axiom of mass moment inertia, right? We know for each rod, the the mass moment inertia about its own mass center is given, right? Right? This for, sorry, for each uh, for each uh, rod, we know that the mass moment inertia about each mass center, just like for this one, for vertical rod, we know it's, we use C1, CH, okay, horizontal, vertical. And this is CH, we know about CV, CH, the vertical, horizontal, the mass moment inertia is given directly. And then we use parallel axiom. And so Ig for the OA, for the vertical rod, I is the mass moment inertia about mass center plus m, the mass, plus the perpendicular distance. The perpendicular distance, okay, will be the mass center of the assembly minus 1, okay, square. And for the BC, same. It's the mass moment inertia plus the total mass times the perpendicular distance from the two parallel axes. Okay, this one will be equal to, sorry, should be here, okay, 2 minus 1.5. And so we can obtain the total mass moment inertia of the assembly. So 10 minutes break and then we continue, okay?